Hello everyone, I will talk about atomic-based integer sum reduction in heap on AMD GPUs. First of all, I would like to thank the reviewers for their comments and the sponsors for their support. Integer sum reduction is a primitive operation in scientific computing. It is true that AMD GPUs have been adopted by facilities and universities for high-performance computing, so it is worthwhile to explore the performance of sum reduction on an AMD GPU. Here is the sequential integer sum reduction of m integers using a for loop in the C-style pseudocode. We can imagine that with the associativity and the commutativity properties of the addition, a parallel implementation divides the operations into independent partial sums. These partial sums and the combination of these partial sums can be performed in any order. HIP stands for Heterogeneous Computing Interface for Portability. It is a C++ runtime application programming interface and kernel language for writing programs, mostly for AMD GPUs. HIP is a strong subset of CUDA in terms of functionality. HIP supports architecture and language-specific features for AMD GPUs. The compiler for a HIP program is available in ROCm, an open software platform composed of tools, libraries, models, compilers, and runtimes. This figure shows an abstract memory model in which a computationally intensive routine kernel is executed to better utilize device resources. A kernel is typically executed in multiple instances. Each instance is considered as a work item for a single element of work. These instances are organized in multiple work groups. The total number of work items in a work group is work group size. A global memory can be accessed by all work items in work groups. A constant memory may be utilized to store constant values across work items in work groups. A work group can take advantage of a shared local memory to enable low latency communication between work items within a work group. A fundamental building block for communication is a barrier function which synchronizes execution of work items in a work group. Enables that all work items have completed an operation before using the result of that operation. This study evaluates the sum reduction on an AMD MI100 GPU. According to the white paper, the GPU replaces hardware resources for graphics tasks with more compute units for high-performance computing. The GPU has 120 parallel compute units. A compute unit is composed of processing elements and memory interfaces. In each compute unit, the scalar arithmetic logical unit operates on values shared by work items and manages all control flow. The vector ALU maintains the vector general-purpose registers that are unique for each work item and executes arithmetic operations uniquely on each work item. Each compute unit has shared local memory that enables low latency communication between work items within a work group. The size of the local memory is 64 kilobytes for each compute unit. The shared local memory contains 32 integer atomic units, enabling fast, unordered atomic operations. Before looking into the reduction kernel, we redesigned the microkernel which were published in the past. Due to the time constraint, I will describe each kernel briefly. For more details, please check out the paper. The first microkernel K1 evaluates the performance of an atomic addition to global device memory from one work item in a work group. The last work item of the work group atomically updates the output in global memory with the built-in function atomic add. The loop count n sets the number of atomic operations the work item will perform. The value of n may be sufficiently large to minimize the side effects of kernel execution, such as coordinated indexing and kernel launch on the performance measurement. The total number of work items in the x-dimensional space, that is global work size, equals the size of a work group. The kernel is expected to be executed on a compute unit. The second microkernel measures the overhead of barrier synchronization with respect to workgroup sizes. The first work item in the workgroup resets the variable sum specified in shared local memory, and then a barrier synchronizes all work items in the group. The global work size of the kernel equals the workgroup size. The kernel is expected to be executed on a compute unit. The third microkernel K3 measures the cost of reduction within a workgroup over shared local memory using one atomic addition per work item. Each work item in a workgroup loads a unique element from an input array in global memory and then atomically updates the variable sum in shared local memory. The global work size of the kernel equals the workgroup size. The kernel is expected to be executed on a compute unit. This figure shows total execution time in milliseconds with respect to the number of loop iterations for the first kernel. Since the total number of atomic operations are the same for any workgroup sizes, the kernel time is not a function of workgroup size, so workgroup sizes are not shown in the figure. The kernel time increases almost linearly from about 27 milliseconds to 267 milliseconds. Hence, the estimated average time of an atomic addition over global memory is about 27 nanoseconds. This figure shows the performance trend for the second microkernel. For a given workgroup size, the time increases almost linearly from 10K to 100K. On the other hand, the increase of execution time occurs at 4 points for a fixed loop count. The conclusion is that the estimated barrier cost increases by approximately 31% from about 35 nanoseconds to 45 nanoseconds when the workgroup size rises from 16 to 1024. This figure shows the performance trend for the third microkernel. The kernel time increases approximately by a factor of 10 when the number of loop iterations change from 10K to 100K. On the other hand, for a given loop count, the kernel execution time increases approximately by a factor of 16.6 when the workgroup size increases by a factor of 64 from 16 to 1024. Hence, the rate of time increase is approximately a quarter of the rate of increasing the number of atomic operations from 16 to 1024. The estimated average time of all threads in a workgroup executing atomic operations over shared local memory is 51 nanoseconds, 73 nanoseconds, 115 nanoseconds, 199 nanoseconds, 370 nanoseconds, 708 nanoseconds, and 1386 nanoseconds for the 7 workgroup sizes, respectively. Now I switch to the reduction kernel. In listing 5, the reduction kernel utilized a shared local memory for storing partial sum results. The first work item in each work group resets the local sum. Then a barrier synchronizes the work item for reading the initialized local sum appropriately. After a atomic add is performed by all work items in each work group, the last work item in the group atomically adds the partial sum to the output. The global work size of kernel is equal to the length of the input array. In listing 6, we generalize the kernel with vectorized memory accesses and vector data types for increasing the efficiency of global memory access and reducing the number of atomic operations of a shared local memory. A short vector type supports a maximum of 4 elements in a vector. To load more elements from an input array in our study, 2 sets of 4-element vector loads or 4 sets of 4-element vector loads are invoked. Since each work item reads a vector in a memory transaction, the vectorized memory access reduce the global work size by a factor of v, where v is a power of 2 ranging from 1 to 16. After reduction over a vector and its partial sum is stored in a register, the number of atomics over shared local memory is also reduced by a factor of v. As an alternative to vectorized memory access, we may increase the workload assigned to each work item. As shown in listing 7, each work item in a work group is assigned the workload of accumulating the numbers read from memory addresses I plus WGS, I plus 2 times WGS, so on and so forth, where I, WGS, and they are the memory addresses for the first integer accessed by each work item in work groups and the work group sizes. The sum of integers is stored in an intermediate variable after atomic addition has been performed by all work items in a work group. The last work item in each group atomic adds this partial sum to the output. RockM offers API that facilitate the implementation of sum reduction for developers. RockThrust provides templated interface to algorithm and data structures designed for parallel computing. Compared to the reduction kernel written in heap, the library-based API promotes programming productivity. HipCub is specific to HIP C++, and its interface explicitly accommodates HIP-specific features. Compared to the RockThrust API, HipCub exposes lower-level implementation details. Fig 5 shows the total execution time in seconds of the vectorized reduction kernel with respect to the workgroup sizes and the vector width for 100 iterations. Nearly linear decrease of execution time from a vector width of 1 to a vector width of 4, and almost no performance improvement across the workgroup sizes from V4 to V16 indicate that V4 is the most effective for vectorized memory accesses. When the vector width increases from 8 to 16, the kernel execution time increases slightly by 1.2% on average. The minimum time is approximately 360 milliseconds when the workgroup size is 1024 and the vector width is 4. Fig 6 shows the total execution time in seconds of the reduction kernels with respect to the workgroup sizes and workload sizes. The performance trends show that the variance of kernel execution time with respect to workgroup sizes is less than 10% when each work item sums up 8 elements. When the workload size increases from 16 to 64, the kernel execution time rises by 7.4% on average. The minimum time is approximately 370 milliseconds when the workgroup size is 512 and the workload size is 8. Hence, the kernel execution time is approximately 3.1% longer than the fastest kernel with vectorized memory access and vector data types. For the reduction implementation with rock thrust and hip cup, the work group size is not exposed as a knob for performance tuning. We find that both implementations rely on the block reduce primitive in the rock prim library as its backend. The default implementation of primitive is reduction in a collection of 64 work items that execute in parallel. The execution time of the reduction kernel for 100 iteration is 368.7 milliseconds and 668.8 milliseconds for the implementations using rock thrust and hip cup respectively. Hence, the fastest reduction implementation with vectorized memory access and vector data types is approximately 2.7% faster than the library-based reduction. For the reduction kernel where the vector width is 4, we generate the instructions of the kernel as shown in here. Due to the time constraint, I will not explain the instruction. Please check out the paper for the meaning of each assembly instruction. Based on the assembly file reports, the total length of the assembly instruction is 192 bytes. Hence, the average size of each instruction is approximately 5 bytes. 12 scalar registers and 6 vector registers are required for executing the instruction. The hardware processor is enabled to solve all data dependencies. The software program helps solve data dependency for a few cases. The compiler can automatically reorder instruction without breaking the correctness of a program. We also measure the average power consumption in watts of running the HIP program with the reduction kernel, achieving the lowest kernel execution time. The power is queried with the ROCm system management interface. For the target GPU, the idle power is around 40 watts, and the power cap is 290 watts. Before kernel execution starts, the spikes over the time interval reach 70 watts as maximum. Then the power increases quickly from 40 watts to 307 watts. The power fluctuates between 277 watts and 300 watts over the period of kernel execution time. When kernel execution is finished, the power decreases quickly from 300 watts to 40 watts. The measurement shows that the power consumption of the kernel execution is significant, although the kernel is not compute intensive. In our study, we designed the microkernel for understanding the overhead of atomic and barrier functions. Then we explained the reduction kernel with vectorized memory access, parameterized workload, and the library-based API. Reading the assembly instruction generated from the vectorized reduction kernel allows us to have a better understanding of the behavior of the hardware. The power consumption of executing the kernel on the GPU fluctuates between 277 watts and 300 watts, while the dynamic power consumption of other GPU activities at most 31 watts. Thank you for listening.